So here's the simplest possible way that you can solve this problem of recognizing a face. So kind of you have a new input face and you want to assign a label to it. So this is called 1 nearest neighbor, and the idea is like this. So let's say that this picture is our new input, and let's say that this is our training set, meaning that we know that this is John, this is John, this is George, this is George, this is Paul, and the last two photos are of Ringo, right? So what we'll do is we'll simply say, well, I'll try to compare this input to this image and the input to this image and so on, and I'll find the image in the training set that's the most similar to the input. So for example, if this turns out to be the most similar image to the input image from the training set, then we'll just look up, well, who is it? This is Paul, so we'll say, okay, this is Paul. It might not be obvious from just those pictures, but this is indeed Paul McCartney of the Beatles, right? So that seems pretty simple. So one question to ask is like, how does it fit into this framework, right? So we said that we're plugging in this new image into H-data, like how's that work? So you can actually fit it into the framework. So you can say that in this case, you're still computing H-theta x, and theta is just the entire training set, right? So the training set is like x1, y1, and x2, y2, and so on, right? So for this particular training set, the procedure is, well, you compare the x to x1, you compare the x to x2, and so on, and you find the x in the training set that's the closest to the input x, and then you output the y that corresponds to that x from the training set that's as close as possible to this x. So the theta in this case, it's not a vector, it's a whole data set, right? And the reason I say that it's the data set is because, well, for a different training set, you would have a different output for any particular x, right? Because it depends on kind of training set, which image from the training set is the closest is as close as possible to x. Like if there is no this particular picture of Paul in the training set, then the output might well be different for the input Paul, this guy. Okay. So how do we kind of like determine which images are similar and which images are not similar? So there are several ways. So in general, because we already know how to convert images to vectors, we can just think about vectors and what makes vectors close together or far apart. So one possibility is to just say, well, like if this is the vector that corresponds to one image and this is the vector that corresponds to another image, we'll just look at the distance between the endpoints of those two vectors, right? So this would correspond to the length of this vector that's connecting pole 1 and pole 2 in this case. So there is a formula for that. So if A is a vector and B is a vector, you can compute the sum of the square differences between the individual coordinates of those vectors, take the square root, and that would be the distance between the endpoints of the two vectors. What's another way you can look at it? Well, you can say, I don't want the distance between the vectors. What I want is the angle between the vectors. So for that, there is actually a formula as well. So there is a formula for the cosine of the angle between the vectors A and B, and it's like that. So this is the dot product of A and B, and you divide by the norm of A times the norm of B. So the dot product is just kind of A1 times B1, A2 times B2, plus A2 times B2, plus A3 times B3, and so on. The norm is just the length of the vector, right? So if the cosine is large, that means that the angle is 0, so the largest possible cosine of theta would be 1, and that would correspond to theta equals 0, so the angle between the vectors is 0, that means they're close together. On the other hand, if the cosine is close to 0, that means that the vectors are orthogonal. That suggests that the vectors are not similar at all, right? So why would we choose kind of one measure over the other? Well, kind of one thing to notice is that if you look at this image, so if you multiply all the pixels here by, let's say, 0.5, what would happen? Well, every one of the pixels would get darker, right? So this would be 30s, and this would be like 128s, and this would be 64s. So everything would get darker, but it's still going to be the same image. So the content is going to be the same, but the numbers, kind of the brightnesses of the pixels, are going to be completely different. So if we do a picture of that, that would correspond to one image being like that, so, and another image, so this would be, for example, the darker image, and then the brighter image would be like that, right? So if you multiply a vector by, so let's say here it would be like 0.2 or something, what you'll get is a vector that's pointing in the same direction, but it's not as long, so the distance between the endpoints could be quite large. On the other hand, the content of the images, in general, would be pretty similar. So that's kind of an argument for saying, in order to compute the similarity between two vectors that represent images, well, maybe in general you want to use the cosine of the angle between them rather than the Euclidean distance, because so that's the distance between the endpoints. Just because, like, you don't care if it's like a darker image or a brighter image. What matters mostly is the contents, right? So that's an argument for using the cosine. On the other hand, sometimes you do care about the darkness. So maybe what you want to do is you want to distinguish kind of night scenes from day scenes. And kind of an important cue for that would actually be not necessarily the content, but the brightness of the image. So it kind of depends. So I want to now take a closer look at the cosine formula. So the formula is cosine. So this would be A dot B, and this would be AB, kind of the magnitude of A times the magnitude of B. So this is the cosine. However, if we say, well, like maybe the magnitude of images is generally all the same. Maybe because I made it so, right? So you can always kind of multiply the image by a constant and make its magnitude be whatever you want to be. So by the magnitude, they just mean kind of the square root of the sum of the squares of the individual intensities of the pixels, right? So you can always like multiply it and force the magnitude to be like 0.5. That would correspond to setting the brightness of the image to a particular value, right? So if we think that all the images are kind of the same brightness, we can say, well, instead of computing this number, maybe we could compute just this number, so the dot product of A and B. And that will give us some indication of how similar or different the images are. So if A dot B is close to 0, that would correspond to the vectors being orthogonal, so not similar. On the other hand, if A dot B is large, that means that the images that are represented by vector A and vector B are kind of similar. Okay, so we'll see how that's useful in a second. So let's look at the specific project for task. So we have 6 actors, so 100 images, 64 by 64 faces each. By the way, kind of the reason they're all kind of similar size is that otherwise, like, you can't compute the dot product of two vectors that are different lengths. So what you do usually is you pre-process all the images to all be the same size. Another issue people often bring up is, well, like, this kind of thing, so like comparing individual pixel intensities, that would work well if the images are registered. meaning that like the eyes are all in the same place, the mouths are all in the same place, because otherwise what you'd be doing when you're computing this kind of thing, like a dot b, for example, which is like a1 times b1 and a2 times b2 and so on, an times bn. So if those pixels don't correspond to similar features on the image, then this kind of formula would not make sense. So it might be easier to think about the Euclidean distance. So this, when it's small, that means that the images are similar. When it's not small, that means that the images are dissimilar. So why is it? Well, because like if all the pixels are literally identical, then you would have a distance of 0, because the distances between the individual intensities for the individual pixels are going to be 0. Now, this kind of thing would not work as well if you move one of the images by just a little bit. So you shift all the pixels to the right or to the left or something, and then even if the context is identical, this distance is not anymore going to be 0 between two images. So think about one image that's like this and another image that's like this, but it's like shifted a little bit. So maybe this is 12 and this is 10. Well, according to this or according to this, the images are not going to be that close. So what you want to do as much as possible is for kind of the eyes to correspond to the eyes, for the nose to correspond to the nose, and so on, and then those kinds of distances start making more sense. You can always, of course, compute the distance. It's just a question of how much it will actually correspond to the contents of the images being similar or different when the distance function is, or the similarity function is larger when the images are more similar and smaller when the images are less similar. So, okay, so here though we have a pretty good data set, right? So, I need to figure out where I'm pointing. Here in the slides, right, all the images are pretty similar in terms of the location of the eyes and so on, so they're registered. So computing those kinds of distances can make sense.